In the previous video, we introduced the ISO OSI reference model. We spoke about the various layers that are part of it, and we also spoke about the principles that are used to let a packet flow through the network, to let one layer of the protocol stack talk logically or conceptually with its peer layer at the destination, but also that the fact that the packet actually flows down the stack on one machine, then at the various routers, perhaps up and down a little bit, until it reaches the destination machine, where it actually flows up the stack until it gets to the highest level, the application layer. In the previous video, we alluded to the fact that every peer layer, so layer 2, layer 3, or layer 4, or whatever, on the machine that is busy sending something, adds a header that is interpreted and then stripped away by the machine that it is talking to at the corresponding layer. So layer 3 will add information that is eventually stripped away at the destination's layer 3. And in the same sense, layer 7, where the real application action takes place, that action will be interpreted by the application layer on the destination machine. In this video that follows, we will go through those 7 layers again. In this case, we will use a short animation to show you how, in each case, what is being transmitted from a higher layer to a lower layer becomes the payload at the lower layer, and then a header, or in some cases, a header and a footer are added. That header contains information that is to be interpreted by the peer layer at the destination, and the peer layer at the destination will also strip away that information and pass the payload up to the higher layer. So rather than just talk about it, let us look at the demonstration that is about to follow. For this illustration, we will assume that 2 computers are connected to one another and they want to communicate. You can see that they each have a network card or network protocol stack running on them. If they had multiple network cards, they might have had multiple stacks, at least up to layer 2. In this case, there's no such problem. We are assuming that there's no routers between them. They are directly connected. However, when we get to the appropriate points, we will talk about the possibility of there being routers between them. So there, in each case, the 7 layers of the ISO OSI protocol stack. On the left-hand side, you can see the names of these 7 layers. At this stage, I assume a little reminder may still be useful, but hopefully very soon we will be able to use that blank space, not for names, and we may actually have been able to indicate where routers may have been present between them. So let's see how these 2 computers can communicate with one another. And we're going to do this by looking at a packet that is formed at the application layer of the left-hand computer. The packet reminds one sort of SMTP, the Simple Mail Transfer Protocol. Yes, we will use things that look like Internet protocols without them really being Internet protocols. It just makes our life a little bit easier if we can cut out some things and assume certain things also. So that's an email message that is being sent. Clearly we are somewhere in the middle of this email session. We've probably already said hello, and after this we will probably send the body of the email. But right now we want to tell the destination who will be the recipient of this particular email. One of the perhaps interesting things in that email address is the use of a domain name xi.net, or some people will prefer to say xi.net, however you pronounce those two Greek letters. Now that is a domain that actually exists. It belongs to me. So yes, I can in fact give people email addresses like those, and it's quite fun to let them try and type that in from a sheet of paper. Yes, it has its uses beyond just giving people who are actually writing email in Greek to use Greek letters. So the challenge with that is that a lot of our networks may not be built to handle Greek letters, so we'll have to do something about that. As a reminder, every layer talks to its peer layer logically. So this email address is what will be given to the layer 7 at the destination machine, but it will not be given physically to the destination machine at this moment. We are rather moving downwards in this protocol stack. So once we've moved down in the protocol stack, we can talk about presentation. And the presentation here presents the problem that we are using those two Greek letters. And as I've said, the network may not be built to operate properly with Greek characters. So the first thing we're going to do is we're going to translate that domain name. One of the rules for domain names is that one is not allowed to have two dashes following one another in a domain name. So in order to internationalize the domain name system, they introduced a special notation to represent the domain names that use international, in other words, non-Latin characters. And for those, they differentiate them from the typical domain names by using two dashes. Therefore, you can see the domain name as translated by the domain name system actually consists of Latin characters, but it uses two dashes, something that would have been illegal, but it's easier to deal with that than to teach the entire network how to deal with Greek characters. Arguably, the more important thing, almost the general lesson that you will see on all the layers, is that we add a heading that tells the peer layer something useful. In this particular case, we said what we have now is something that is encoded in ASCII. We are talking to layer 6 yet again. In the real life, we are therefore telling this destination machine that what follows is encoded in ASCII. In the real world, we won't really use ASCII as an indicator. We will rather use one of the ISO standards that standardize various character sets, including ASCII. But it's easier for this example to fit in ASCII, the acronym ASCII, than to write a whole ISO specification number in there. So logically, we have now told the presentation layer we have something encoded in ASCII, and the presentation layer on the receiving end will be able to look at that, see, I know what that means, and it will be able to translate it back to the Greek characters when it passes the message up to layer 7 at the destination side. However, we are sending this message downwards as we always do, except in the case of layer 1. On layer 5, the packet that has arrived from above becomes the payload, and we're going to add a header. Layer 5 is a very difficult one to provide proper examples for because, as I've said previously, we don't really use it. In a sense, we are dealing here with a simple mail transfer protocol. So what it means is we have already said hello, and after we've said from whom this mail is coming, we will probably also include the email and eventually quit. So I'm going to add a header that doesn't help much, but just to be consistent, I'm going to add it. And the only thing that this header states is that we are in fact in the middle of some email session. The session is active. It's also possible for some of the other protocols where you may have to log in, and then after you've logged in you can, for example, transfer files, that the header may say that we are indeed logged in. Now, life isn't always that simple, because if it's a matter of adding a header to say that we are logged in, lots of hackers will just add headers to say that we are logged in. So we need something more, but this is good enough for our illustration. So we are going to tell peer node on the receiving node that we consider ourselves as being logged in. The message goes from this machine's layer 5 to the receiving machine's layer 5. But as always, the actual message moves down the protocol stack and becomes the payload on layer 4. On layer 4, we will yet again add headers, as we basically do in all instances. You can see that we've taken our example sort of from the TCP protocol, so it's again sort of internet-like. It's the easiest example to use because it's the one that you are most familiar with, even if you've not really worked with networks on this level yet. So what you can see there is we've added in the header that the destination port is 25. In other words, what we are telling the receiving layer 4 is that this message, this packet that we are constructing, is intended for the email server, because the email server, more specifically the SMTP server, will be waiting on port 25 for us. The source port will be an ephemeral port or a temporary port or a dynamic port, just one of those high-numbered ports that we tend to use for all sorts of purposes. We need a port number so that the server can talk back to us, so that it can, when it replies, use something as a destination. So we are giving these two ports logically to the destination server. The destination server, the destination machine, will be able to interchange the two and send the reply back to port 55555, where our client will be waiting, and it will be coming from the email server, whatever response is coming. So it will be coming from port 25. Yet again, in the real world, we are not talking to our peer really. That's our intended recipient. But the actual packet moves down the protocol stack and becomes the payload on layer 3. So to become the payload on layer 3, we are going to add a header, and since the network layer deals with routing, it makes sense that the header that we add will consist of addresses. It will also have other information. This is by no means intended to be a complete example, but let's add the header that at the very least consists of the two addresses, the source address and the destination address. You can see that those addresses, we've sort of taken the notation from IP addresses, but those are not real IP addresses. We've just picked out something that looks like an address just for the purposes of our example. So our network layer can now logically talk to its peer, and this is the very first case where its peer may actually be one of the routers that may be situated between these two machines. So what will happen here is this message will go out logically to its peer layer. Its peer layer may be the first router who will look at the source and destination addresses, especially the destination address, and it may send it on to another router, and that router may talk to another router, and in these cases the first machine is a peer of the router, first router is a peer of the second router is a peer of the third router, and then eventually whichever router happens to be the last one is the one that talks to the destination machine's layer 3, where the destination machine will then say, this is my address, and I'm no longer going to pass it on to other machines. I am rather going to pass it up the protocol stack. Yet again, logically, we are talking to this potentially series of peers between us and the destination node. But in the real world, we are moving down the protocol stack where this message will become the payload on the next layer down, in other words, on the data link layer. On the data link layer, we are going to add a header. But the data link layer is special in the sense that we very often also add a footer. And the reason why we may want to add a footer, one of the major reasons, is that we may want to delineate this packet when we send it across the wire. And we'll talk quite a bit about data delineation later in the module, but for the time being, let's assume that we put some special marker at the front and some special marker at the end, so that when we do send it across the network, we can see where this package begins and where it ends. And if we see any data between two packets, that's just garbage, it's just noise, we can ignore it. So here, let's keep this payload and then add these two markers. There it remains the payload. There we have added the two markers that we've simply called begin and end. We are yet again sending this to layer 2. And one of the things that we've been saying all along is that layer 2 will use the information that we've added, but it will also strip it away. In other words, layer 2 on the receiving machine will see that we have sent this message that has now been encapsulated, it's been demarcated. Typically we will say it's been delineated. This is where it starts, this is where it ends. So layer 2 on the receiving machine will be able to see the beginning and the ending marker, and then everything between those two will be the real message. So layer 2 on the receiving end will strip away this header and this footer that we've added. We'll see it happening just now when this message arrives at the receiving host. Logically, we're going across to the peer layer, and here, just as an aside, the peer layer will be the thing that sits at the other end of our connection. So if we are using a copper cable, it will be whatever router or destination machine is connected to the other end of this copper cable. Actually, we may have multiple machines connected to copper cable, but no matter what, the peer that we are talking to is something that will be physically connected, and if this is routed, it will be routed out via another link. We've used fiber optic cables in some of our examples in the past, so it may arrive via copper at this router, and then once the network layer sees that it needs to be routed further, the network layer may send it down a stack that is connected to an optical fiber, and that layer 2 from the router will then connect it to another machine via the optical fiber, and it will use its own data link layer protocol to talk via the optical fiber to the next machine in the chain. So this is really from one point to the next. A certain data link layer protocol will be used, and then from that point to the next, another data link protocol layer will be used, and yet another protocol on the next link, and so on. And across all these various links, different protocols will be used, or the same if it happens to be the same sort of cable, but eventually it will arrive at the destination machine where once it hands it up to layer 3, it will simply deal with it. Layer 3 will send it upwards and it will not be transmitted or relayed any further. Again, this is actually sent down the protocol stack. In all our examples, we have added headers and footers. The physical layer is a bit different. It may take what we have and translate it to some physical representation, for example, high voltages and low voltages and so on, and may even add headers in terms of high voltages and low voltages. But at this stage, it is no longer something that is humanly readable. It is something that is electrical, and we're going to try and indicate that by adding a waveform here. The message is translated to that waveform. Clearly, we need many more bits for a typical message, but that's good enough to fit it in here. Now, where this is different, this is not going to be able to send it any lower. It will now send it via this physical connection that connects the two machines, or at the very least across the first hop to the very first router. Let's assume the two machines are indeed connected, and it sends this message in binary form from one machine to the next. There you can see the message on the wire, and then at the destination machine it is accepted on the physical layer again. On the physical layer, it will take whatever has arrived and it will translate it into the appropriate binary values, and that will go up to layer 2. So what we will see on layer 2 once this is being processed should be exactly what we send away on layer 2. On layer 2, you can see the markers that we've added, the begin and the end. There could also have been lots of other things that we've added, and when we talk about layer 2 protocols, we will talk about those things that can indeed be added as headers and perhaps as footers as well. However, layer 2 on this receiving end strips away the begin and the end markers, those delineation markers. It takes the payload and it passes it up the protocol stack. What arrives on layer 3 eventually is what we have sent away on layer 3 at the origin. You can see the addresses are encoded, and in particular, since we are now at the destination machine, this computer will say, I am machine number 192.5. This is intended for me. I'm not going to send it to any other router or anything. Since it has reached its destination, I can simply discard the addresses. I don't need those addresses anymore. Yes, when we respond a little bit later, we will use those two addresses in reverse order. So the response will be sent to the source address, and we will use this machine, in other words, the destination address, as the source address for our return message. But as far as the network is concerned, we can now discard those, and the payload is sent up to the next higher level on the protocol stack. On this next higher layer of the protocol stack, we see the information that we use to dispatch it. So we see that the destination port is 25, the source port was the 55s, and at this stage the transport layer knows that this is intended for the email server. It's going to discard this information. Yes, maybe it will keep a note, because if we respond just now, then the destination and source ports will again be interchanged. For the response will come from port 25 and be sent to 55555, but we can forget about those now. Simply take this payload and pass it up the protocol stack. Here we are back on layer 5, and we have that header, the one that we said we are really using just to be consistent. it's of very little help in this example, but we will do exactly what we've done in the previous cases. We will process it for whatever processing is required, strip it away, and then the payload will be sent up the protocol stack on this side. Layer 6, the presentation layer, will see that whatever we have received here is represented in ASCII, so it's a normal Latin alphabet. There won't be any Japanese characters or anything strange in there. Of course, if the Japanese build computer systems, they can encode everything in Japanese. It's just the convention that you use. Maybe our presentation layer is intelligent enough to handle different encodings. And this one, or this header, simply tells it, this is in ASCII, so use your ASCII decoder to take whatever has arrived and then pass it up to layer 7, the application layer. So once it's done that translation from ASCII to whatever the email server actually needs, it will discard the information that its incoming message was encoded in ASCII, and it's only the payload that will be passed up to layer 7. At layer 7, we at long last have that message that comes from this rather strange email address, and the conversation can now continue in the sense that the receiving machine may say, okay, I like that. Here is a 200 series error message to tell you that I received this and all is well. So it will then, down each stack, begin to pass the 200 message. Eventually, it will cross that physical connection on layer 1 to the machine on the left-hand side. It will move up the protocol stack all the way up, and the application layer will know that the next message that it can send is the receipt 2 or recipient 2. And it will then come down the stack again, move up the stack at the receiving machine, and this will continue until the entire message has been transmitted and the connection is broken. The application layer is satisfied that it has actually sent out its message. The two important things that almost become the same thing that you've seen illustrated here in a lot of detail is every time that a message goes down the protocol stack, it becomes the payload and a header is added. And then whenever the message arrives at the destination, the header is interpreted and the payload is taken and pushed up the protocol stack until it gets to layer 7 on the receiving end. This is a really, really important concept to understand, so hopefully this explanation made it clear enough for you to be able to talk about it without any hesitation. Now that we've looked at the progression of a packet through the ISO OSI reference model, it is time to make it somewhat more realistic by looking at real packets that we find on real networks. The way in which I'm going to illustrate this is by using a program known as Wireshark. Wireshark is a program that will eavesdrop on a network. It will wiretap the network in a certain sense and lift all the information it can from that network. Now, the way that most networks are built nowadays, you will only be able to get traffic that comes to you or goes from you. So it is no longer the spy tool that it perhaps once was, where you could eavesdrop on other people's information. Although if you have the appropriate authorizations on key parts of the network, you can still do that. Something to keep in mind is what the law says about the use of a tool like this. In South Africa, we use one-party consent. So if I am a party to communications, then I am allowed to record it. In other jurisdictions, you may have two-party, or you may need two-party consent, and then you may need to get permission from the other party, the party with whom you are communicating, to capture the traffic. In this particular case, I'm also using my own private network, which makes life a little bit safer in terms of not capturing other people's traffic. So just double check what the law says in your jurisdiction before you go ahead. Now, to go ahead, you simply download the program known as Wireshark. It is a tool that is used all over the world to do network troubleshooting. I strongly recommend that you use this tool once you start writing your own software as part of the practical sessions, because you will be able to see what flows across the network using it. And if your program doesn't work, then again, it's much easier to solve the problem if you know what is actually being transmitted across the network. In the little demo that is about to follow, we will simply let the traffic flow a little bit, capture some parts of it, and then go and explore what it can show us about those parts. Let's take a look. Here we have the Wireshark interface. I know this is too small for you to read, but let me just point out a couple of highlights. We will zoom in very soon so that you should be able to read what's happening. Right at the top here is the capture interface that asks me which interface do I want to capture. And if I had some previous captures that have been saved, they would have been listed at the top, and this list of devices, of interfaces, would have been displayed somewhat lower. I'm going to select Ethernet, and the moment when I select it, it will start capturing it. Just before I do that, next to Ethernet, you may see, once you do this on your own machine, that there is a little wavy line or there's a straight line. If it's a straight line, it means there's no traffic, there's nothing happening on that. But if you can see some sort of a wavy pattern, it means something's happening, and on this Ethernet adapter, something is indeed happening. So let's pick that, and then you can see it starting to capture at the moment. I'm going to stop the capture immediately because I don't want a long capture to be made here, but in principle I can let it run for quite some time. In this top pane, where I'm moving the cursor now, there you can see all the packets that have been captured, and it's just the headings, it's just the highlight portions of the packets that are shown there. In the next part, where I'm moving the cursor now, the middle pane, there you will see details of the highlighted packets. The moment when I highlight a packet in the top pane, there is a possibility, and if you watched carefully, you would have seen this change. Let me pick another one there, and I'm going to click on that, and you will see that the packet changes here, all the details of it. In this bottom pane, you will see the hexadecimal and also the string rendering of the packet that I have just highlighted. So let's try and make this a bit more legible for you and zoom in somewhat. So what I have here is the packet that I have highlighted is the packet that you can see there at the bottom of the top pane. Now what I can do here is I can move the line between the two so that it becomes a bit clearer, and that packet, that 1290, is the one that I'm talking about. I can even move the headings out a little bit so that you can see the relative time at which it was captured. There is the source address from which it originated that is being revealed now, and there is the destination address and the specific protocol. And okay, messed it up, doesn't matter. The point is that normally you would not have to enlarge this as much, and in enlarging this I am actually losing information on the right hand side of the screen. So the packet that I've highlighted, let's look at that on this middle pane. And what is important here is to see the layers. So you will see that each of these lines represent a layer. Unfortunately, these are the TCP IP layers. They are not the ISO OSI layers. So here in this particular case, there is no application layer that has been highlighted. So that would have been right at the bottom. Layers 5, 6, and 7 in the ISO OSI model would typically be grouped together in the application layer. But since it's not obvious which application is running here, it does not show me something. So this transmission control protocol, TCP, there you can see the ports that are being used. So we are on layer 4 of the ISO OSI reference model. I can open it up and it will show me more information about this. I can scroll through it. The details are not important right now, but the fact that you can start to play with this is important. Just below that is layer 3, the internet protocol. So this does routing. You can see the addresses highlighted there. And in fact, if I were to click on this little arrow to open it up, then you can very clearly see the source address and the destination address and all the other things that are highlighted in here. We will talk about those details later on, but I'm going to close this again. Now, where this behaves somewhat differently from what we would expect is it divides layer 2 into 2. So there we see an Ethernet part of it, and there we see a frame part of it, and it does not show us the physical layer. So the layer 2 upper and lower parts, if we open up the upper part, there is some information about it. And similarly, if we open the lower part, the part closer to the physical layer, there is some information about it. Again, I'm not going to look at this in any detail. So we can also look at the hexadecimal representation. In particular, if I pick out anything at the top here, it will highlight the hexadecimal representation for me, and I can look at that in more detail. But for most of what we're going to do, we're not going to be too interested in the hexadecimal portion. Here is another packet that I've captured. You can see that this one does indeed, in this middle pane, indicates that it is the Hypertext Transfer Protocol, HTTP. If we were to open that one up, then you will see the web page that we were asking for, what is the full request, and so on, and all the other information about the HTTP request. Not going to go through that in any detail, but that then is the application layer, but together with that also the session layer and the presentation layer. Below that, again, the transmission protocol, as we've seen previously, with source and destination ports indicated. We have the internet protocol, as we've seen before, and then the upper and also the lower part of layer 2. In this video, we considered an animation that showed us the progression of a packet through the 7 layers of the ISO OSI reference model, from layer 7 down to layer 1, across the physical medium, and then up the 7 layers at the destination machine. At the destination machine, traffic will obviously then be able to return by flowing down those 7 layers via the physical link and up the 7 layers at the original sending machine. We also introduced Wireshark as a tool that you are expected to use in the remainder of this course to look at the software you develop, and in particular to look at the packets that flow via the network. I strongly encourage you, after just thinking about the legal implications, to immediately get Wireshark and begin to explore how to use it and begin to explore what you can observe, because there are lots and lots of interesting things that one can observe in a network. Some of the protocols that we won't even talk about may catch your eye, and they may turn out to be very, very interesting. However, in due course, we will also talk to you about how you can narrow what you capture or what you search for. Life will be simpler once we learn how to set the program up so that it only captures the information that is relevant to us. In the meantime, however, capturing all that interesting information, strange though it may be, is a very, very useful tool to explore networks, and I really encourage you to start looking at that. In the next video, we start with the protocol stack. We will start at layer 7, and then, as promised, we will move down through using various videos on every layer, move down from layer 7 right down to layer 1, and that will eventually complete the module. See you soon.